Why are intermolecular forces important for real gas calculations? Imagine trying to predict how a gas behaves when you squeeze it into a small space or cool it down. It's not as simple as just counting particles and applying a basic rule. That's because in real life, gas molecules do more than just bounce around randomly. They actually attract and repel each other through forces called intermolecular forces. These forces are tiny but powerful enough to change how gases act under different conditions. When gases are at high pressure or low temperature, molecules get closer together. At these distances, the assumptions of the ideal gas law, that molecules are point particles with no volume and no interactions, no longer hold true. Instead, the molecules take up space and start pulling on each other. These attractions cause the gas to deviate from the predictions of the ideal gas law, which can lead to errors if you don't account for them. That's where more advanced equations come into play. The van der Waals equation is a common example. It adjusts the simple ideal gas law by adding terms that account for the volume of the molecules themselves and the attractive forces between them. By including these factors, the equation gives a much more accurate picture of how gases behave, especially under conditions where the molecules are packed tightly or cooled down. Why does this matter? Well, if you're designing equipment like refrigeration systems, industrial compressors, or even scuba tanks, using the ideal gas law alone might give you wrong estimates. These errors could lead to safety issues or inefficiencies. Real gas equations help engineers and scientists make precise predictions about pressure, volume, and temperature, ensuring everything works smoothly and safely. Think of it like traffic flow. If you imagine cars as points that never interact, traffic would always move perfectly. But in reality, cars have size and drivers react to each other. They slow down or speed up based on what others are doing. Real gas equations are like traffic models that include car size and driver reactions, giving a truer picture of what actually happens on the road. So, intermolecular forces are key for real gas calculations because they explain why gases don't always follow the simple rules. By considering these forces and the size of molecules, scientists and engineers can better predict how gases will behave in different situations. This makes thermodynamic calculations more accurate and practical, helping us design safer and more efficient systems that relying on gases.